Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders 2014, problem number 1. Let Fn, going from the compact interval 0n into the set of real numbers, be defined by this equality. Fn of x equals arctangent of floor of x. We wish to prove first that Fn is Riemann integrable for every positive integer n, and then we wish to compute the following limit. The limit as n goes to infinity of 1 over n times the integral from 0 to n fn of x dx. So it's a nice problem involving some calculus. Here are my hints. First, you should realize, you should be familiar with this fact that every bounded function defined over a compact interval which is continuous everywhere with exception of finitely many points, is Riemann integrable. In fact, much more can be proven, namely, if bounded function defined over a compact interval is continuous almost everywhere, that means that the Lebesgue measure of the set of points of discontinuity of our function is of measure 0. Also, in this case, our function is Riemann integrable. This is just a special case. It is called Lebesgue-Vitali theorem. So, okay, then I suggest that you first compute the integral by splitting the interval of integration into pieces from one integer to another integer and summing them together. And finally, this theorem will be very useful to compute the limit. Stolz-Cesàro theorem, which says that if we have two sequences, an and bn, are sequences of real numbers, and if sequence bn is strictly increasing, it diverges to plus infinity, and moreover, if the limit of differences, this delta an, if you are not familiar with, delta an means n plus first term minus an. If the limit of these differences exists, then the limit of an over bn also exists and is equal to the limit of these differences. It's a discrete analog of the L'Hopital's rule. So give this problem a try and I will see you in just a minute. Right. So let's start with our function. Notice that floor of x is discontinuous only at integers. So our function fn, going from the set of from 0 to n, taking number x and returning arctangent of floor of x, this function is discontinuous only at what points? At 1, at 2, and so on, at n minus 1. Finitely many points. Moreover, it is bounded. Moreover, it is weakly increasing. So it is bounded. Yes, because the floor of x is weakly increasing, arctangent is strictly decreasing, so after composition we have a weakly increasing function, which is bounded from below by f of 0 and from above by f of n. That implies that fn is Riemann integrable. Pretty nice explanation, I'd say. And now let's tackle our limit. So first of all, we'll tackle the integral from 0 to n of f n of x dx. So it's integral from 0 to n of arc tangent of floor of x dx. And now to get rid of this floor function, I will split this integral into pieces. From integer k to another integer k plus 1, and I will be summing them together. This can be done because it's a sum of only finitely many subintervals. Arc tangent floor of x. And now let's note the following thing, that if x is between k and k plus 1, then floor of x equals just k. It's actually constant. So on every interval, our floor of x is actually k, and it is independent on x. We have sum going from k equals 0 to n minus 1 of arc tangent k times integral from k to k plus 1 dx. And of course, the integral of 1 is just the length of the interval of integration. So we have just sum going from 0 to n minus 1 of arc tangent k, because this integral is 1, because the length of the interval is 1. Very well. And now notice the following. I will use Cesàro-Stolz theorem. Note that if maybe note that the following is true. Well, difference operator on this sum k over difference of n, what is it? Well, we are taking difference, so the difference in the numerator will be sum going from k equals 0 to n of arc tangent of k, and we are actually subtracting sum going from k equals 0 to n minus 1 arc tangent k. Sorry, let's move this to the left. Oh no. Yes, very well. And the difference in the denominator is just n plus 1 minus n. And notice that in the numerator we are left with arc tangent of n. Well, and the denominator actually disappears. And we know that arc tangent of infinity is pi over 2. So this converges to pi over 2 as n diverges to infinity. Moreover, sequence n from n equals 1 to infinity is strictly increasing, obviously, and diverges, which means that we can actually use a Stolz-Cesàro theorem. By Stolz-Cesàro theorem, we know that limit as n goes to infinity of our sums tangent k over n, it's actually pi over 2. And that is our answer. We can write our answer once again, that the limit as over 1 over n times the integral from 0 to n of fn of x dx, this limit actually equals pi over 4. Pi over 2, sorry. And that closes our problem. A very nice problem given to 12th graders in Romania. So if you are not familiar with this theorem, I recommend that you look it up on Wikipedia, for example. It's a discrete version of the L'Hopital's rule, because in the L'Hopital's rule, we are taking derivatives in the numerator and the denominator, and in Stolz-Cesàro theorem, we are taking not derivatives, but actually differences. So difference between two consecutive terms of a sequence. And that is it. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.